Download this code from codegive.com, link in the description below. Deep copy behavior in Python 3.9 and beyond, recursion error and how to avoid it. In Python 3.9 and later, the behavior of copy.deepcopy has changed, particularly when dealing with recursive data structures, objects that contain themselves, directly or indirectly. This change can lead to a recursion error where it didn't previously occur, or make it more difficult to deep copy complex objects. This tutorial will dive deep into this change, explain why it was introduced, provide code examples showcasing the issue, and demonstrate various strategies to avoid it and safely deep copy recursive structures. 1. Understanding deep copy and recursive structures. Before we delve into the specific change in Python 3.9, let's refresh our understanding of deep copies and recursive structures. Deep copy. A deep copy creates a completely independent copy of an object and all its sub-objects. Modifying the original object or any of its sub-objects will not affect the deep copy, and vice versa. This is in contrast to a shallow copy, which creates a new object but references the same sub-objects as the original. The copy.deepcopy function in Python's copy module is used to create deep copies. Recursive structures. A recursive data structure is an object that refers to itself, either directly or indirectly through its members. Examples include direct recursion, a list where one of its elements is the list itself. Indirect recursion, a dictionary where a key maps to another dictionary, which in turn maps back to the original dictionary. Objects with self-referential attributes, an instance of a class where one of the attributes refers to the instance itself. 2. The change in Python 3.9, a deeper dive into memoization. The core change in Python 3.9 involves how copy.deepcopy handles memoization, caching, during the deep copy process. Pre 3.9 memoization. In versions prior to 3.9, deep copy used a dictionary, called the memo dictionary, to track objects that had already been copied. This memo dictionary mapped the object identity, i.e., the ID, of the original object, to its corresponding deep copy. This prevented infinite recursion when encountering recursive data structures. If deep copy encountered an object that was already in the memo, it simply returned the already copied object instead of creating a new copy. The shallow copy of the object was stored in the memo. Python 3.9 memoization enhancement, and the problem. Python 3.9 significantly altered the memoization process for performance and correctness. Instead of storing the shallow copy, deep copy now stores a weak reference to the original object in the memo. This allows the garbage collector to reclaim memory used by the original object even while the deep copy is being created. This change was made to address potential memory leaks and improve efficiency. Why does this cause problems? The switch to weak references in the memo dictionary causes recursion error in recursive structures because 1. Garbage collection and weak references. Weak references allow an object to be garbage collected even if a weak reference to it exists. If the original object is garbage collected during the deep copy process, the weak reference becomes invalid. 2. Repeated object copying. When deep copy encounters a weak reference in the memo that has been invalidated, meaning the original object was garbage collected, it no longer recognizes that it has already processed that object. Therefore, it tries to deep copy the object again, leading to an infinite recursion. 3. Recursion depth exceeded. The repeated deep copying of the same object without termination quickly exceeds the maximum recursion depth limit set by Python, resulting in a recursion error. 3. Code example demonstrating the recursion error. Here's a classic example that triggers the recursion error in Python 3.9 and later. Explanation asterisk. 1. We create a recursive list where the list itself is an element of the list. 2. We attempt to create a deep copy of the list using copy.deepcopy. 3. In Python 3.9 plus, this code will almost certainly raise a recursion error. Deep copy enters an infinite loop trying to copy the list, because it keeps encountering the original object which has been weakly referenced. Since the original is never fully copied, the weakref becomes invalid, causing a recursive loop. 4. Strategies to avoid recursion error and safely deep copy recursive structures. While the change in Python 3.9 introduces a challenge, there are several strategies to overcome it and deep copy recursive structures safely. Strategy 1, copy_reg, for custom classes and complex scenarios. The copy_reg module, formerly copy_reg in Python 2, allows you to customize how copy.deepcopy handles specific classes. You can define custom pickling and unpickling functions that explicitly manage the recursion. This is the most flexible but also the most complex approach. Explanation asterisk. 1. Reduce_node, node, asterisk. This function defines how a node object should be pickled, saved. Crucially, we store a weak reference to the next node rather than a direct reference. This is key to preventing the recursion. We store the state of the object, in this case, just the next node, in a dictionary. 2. Reconstruct_node, CLS, value, state, asterisk. This function reconstructs the node object when it's unpickled, loaded. It uses the weak reference to the next node, if it exists, to re-establish the link. Notice we dereference the weak reference using state next, which then stores the pointer to the object. 3. Copy_reg.pickle, node, reduce_node, reconstruct_node, asterisk. This registers the reduce_node and reconstruct_node functions with copy_reg for the node class. Now, whenever deep copy encounters a node object, it will use these functions to handle the copying process. Advantages asterisk. Asterisk. Precise control over how specific classes are deep copied. Asterisk. Allows you to break recursive loops explicitly. Asterisk. Robust and adaptable to complex object structures. Disadvantages asterisk. Asterisk. More complex to implement than other strategies. Asterisk. Requires intimate knowledge of the class's internal structure. Asterisk. Requires using weak refs which might be confusing. Strategy 2, iterative deep copy with explicit stack, manual memoization. Instead of relying on copy.deepcopy, you can implement a deep copy function manually using an iterative approach with an explicit stack and a memo dictionary. This provides fine-grained control over the copying process and allows you to handle recursion directly. This approach simulates what deep copy used to do before the 3.9 changes. Explanation asterisk. 1. Deepcopy_iterative, obj, memo equals none, asterisk. This function emulates the behavior of copy.deepcopy, but uses an explicit stack to avoid recursion. The memo dictionary stores the mappings between original objects and their deep copies, just like the internal deep copy uses. 2. Stack-based traversal asterisk. The function uses a stack to keep track of the objects that need to be processed. The stack stores tuples of object ID, object, shallow_copy. 3. Handling immutable types asterisk. The code immediately copies immutable types like numbers, strings, and booleans because they can't be mutated, and creating multiple copies of the same value is safe and efficient. 4. Handling mutable types asterisk. For mutable types like lists and dictionaries, the function creates an empty object of the same type and saves it into memo. Then it puts all the subcomponents onto the stack for processing. When the stack is unwound, the objects are built up and inserted. 5. Handling user-defined objects * for custom classes. This example initializes a new instance using type obj __new__ type obj, copies attributes iteratively using vars, and processes recursively those attributes via the stack. 6. Checking memo *. The function checks if an object has already been copied using memo. If so, it retrieves the already copied object and returns it, preventing infinite recursion. Advantages * provides complete control over the deep copy process. * avoids recursion and recursion error explicitly. * can be customized to handle specific object types and recursion patterns. Disadvantages * more complex to implement than using copy.deepcopy. * requires careful handling of different data types and object structures. * requires understanding of Python object model, attributes, identity, etc. Strategy 3, Limiting recursion depth, a limited solution. You can increase the recursion limit using sys.st recursion limit. However, this is generally not recommended, as it can lead to stack overflows and other issues. It only postpones the problem, and you still need to carefully manage the potential for infinite recursion in your data structures. It's also not a safe or reliable solution. Advantages * simple to implement, just a single line of code. Disadvantages * only a temporary fix. * does not address the underlying issue of recursive structures. * can lead to stack overflows if the recursion depth is still too high. * is generally not a good practice. Strategy 4, Restructuring the data, the best approach. The most effective solution is often to restructure your data to avoid recursive structures in the first place. This might involve using alternative data structures or representing relationships differently. This can often be achieved by storing objects as IDs and only loading them when absolutely needed. For example, instead of having a direct reference to a child object, you could store the child's ID and retrieve the child object on demand, using a lookup table or database. Example, circular linked list. Instead of using node1.next equals node2 and node2.next equals node1 to form a circular reference, store the IDs of the nodes. Advantages * eliminates the root cause of the recursion error. * improves the overall design and maintainability of your code. * often leads to more efficient memory usage and processing. * allows for easier serialization and deserialization. Disadvantages * might require significant changes to your existing code. * can make certain operations, example traversing a linked list, slightly more complex. 5. Conclusion, choosing the right strategy. The best approach to handling recursion error in deep copy depends on the specific situation. Restructuring data * if possible, restructure your data to avoid recursive structures entirely. This is often the most elegant and maintainable solution. Copyreg module * if you need precise control over how specific classes are deep copied, and restructuring is not feasible, use the copyreg module to customize the deep copy process. Iterative deep copy * if you need full control but don't want to modify your class definitions or use copyreg, implement a deep copy function manually using an iterative approach with an explicit stack. Limiting recursion depth * avoid increasing the recursion limit as it only masks the problem and can lead to other issues. By understanding the changes in copy.deepcopy, behavior in Python 3.9 and beyond, and by employing these strategies, you can effectively avoid recursion error and safely deep copy recursive structures. Always prioritize restructuring your data to avoid recursion when possible, as this will lead to the most robust and maintainable code. If restructuring isn't an option, the copyreg module and the iterative deep copy approach provide powerful tools for handling complex recursive scenarios. Remember to carefully consider the trade-offs of each approach before implementing a solution.